Hello, James. This is all basically going to be just randomly put together. So if it's a bit hodgepodge, then it basically is hodgepodge. I'm going to quickly crap magnetic fields. Magnetic fields, basically, if you know, there is basically a magnet. So one's got to have North Pole, one's got to have South Pole, and you've got basically this invisible force that is expressed in some sort of field, okay? And these are your magnetic fields, and they're running from north to south. So you do it that way. And essentially, one of the strange things about magnetic fields is if you try to break this magnet into two, so if I did that, you'd think that these fields are basically going to just snap apart as well, and you can end up in this situation. But yeah, like I said, in physics we don't totally understand this, but this situation we have right now is called a monopole. Um, we do not have any monopoles scientifically. If you discover a monopole, then you've pretty much struck it big. But the moment you break a magnet up, essentially, you just get two magnets. So scientifically, magnetic monopoles don't exist. In theory, they do. Technically, kinda. But yeah, just for the sake of A2, they don't exist. They're not possible. Moving on from that, you also need to know about, or you need to know that a wire with a current in it will also have its own magnetic field. And if you remember right, it's just this sort of circular thing that spans outwards. So the further you get from the wire, the weaker it gets. For that, you probably use the sort of thumb rule, where you basically stuck your thumb in the same direction as the wire, and where your thumb turns in is the direction of the waves. So because my current's heading upwards, my magnetic field is going in this direction like so. That's probably what you learn at GCSE. So we'll expand it a bit in a situation where we've got basically now a magnet here. Let's say that's a North Pole, and likewise, let's say this is a South Pole. South. Your magnetic field is gonna be running like this. So let's imagine that now we have a piece of wire. I'm going to draw it like this, and essentially if I cut that down and across, every time I cut through those fields, something's going to happen. It's got a current through this as well. So because this wire has a current, like I said, if it carries a current, it's going to have its own magnetic field. So we have basically two magnetic fields interacting with each other, and it's causing something to happen. Essentially, in the same way that you have two north poles coming together, the magnetic fields will repel each other away. You've got that same situation happening when you have a current going through a wire and a wire going through a magnetic field. It's going to do Fleming's left-hand rule. So you've got this situation where you want to do something like that. So there's your hand. Your thumb is going to be F. Your index finger is going to be your B, and that's your force, or some people are going to call it your motion, essentially. But you need a force to put yourself into motion. I go F. Like I said, people are going to say motion. That B is for basically magnetic field. So B is the symbol for magnetic field. In particular, it's the magnetic field strength. Okay, so the magnetic field strength is determined by basically how many lines you have. So the more lines you have, or field lines, the stronger your magnetic field strength. And this little dangly bit here, that's caused by this bit here, is I. That's your current. The way I remember it is I need to get my left hand and looked like that. And then I got my right hand, held it over like that, and pretended that was Uzi. It works. So yeah, the way I remembered it as well was it's an Uzi, and the FBI use Uzis. Um, yeah, it's just something I carried forward. That's typically something you learn from GCSE. The only thing that you do need to know is the magnetic field strength. The SI units for that is basically a Tesla. Okay, the Tesla is basically described as something that's WB over meter squared. You know what meter squared is? It's an area. That WB, I'm trying to remember what it's called. It's Webler, something like that. Um, it's a weird one, but that there is, well, that unit there is basically flux, or the flux density. Or actually, it's just flux. It's just flux. And I think that's the bit that's confusing, magnetic flux. So before I move on to magnetic flux, I should probably talk about basically what happens when you've got a charged particle now in magnetic field. Okay, the best way to describe this is sort of to draw you an example. So I'm gonna draw. I'm gonna draw you something that I saw as an A-level student. So we had this big thing here. We had basically this bit here basically shot electrons. So you get electrons coming up through here, and all of a sudden they meet this wall there, and when it hits that, it basically causes some sort of radiation. The radiation it caused is basically this green light radiation. There's another part to this. Hanging inside this glass vacuum jar type thing was something called a Maltese cross. So this Maltese cross was actually blocking. Sometimes they have holes in. I'm going to put the hole here. But that Maltese cross is actually blocking some of the electrons. So the pattern we see is essentially this green light with this Maltese cross missing. Okay, and the reason I'm bringing this up is because essentially all of this is some sort of charged particle phenomenon. So these electrons are hitting this part here. I honestly can't remember, it was 2 ages ago. But high energy electrons are essentially rammed into this edge, and it causes some sort of decay. It might not even be a decay, it might just be just high energy versions of these electrons giving out radiation. But we see the phenomenon as a green light, and like I said, there's this cross hanging inside this vacuum, glass vacuum thingy, that blocks off some of the radiation. So we end up with this sort of shadow in this green light. And like I said, this is all charged particles. When I start introducing, say, a magnet, if I bring that closer to this particle, what happens is this magnetic field here is going to start interacting with these charged particles. The phenomenon itself, I'm going to show you it here. Here's it, or here it is as a Google image. Can't really see it, but essentially you can see here where the mouse is. There's the guy's the guy's magnet. There's the guy holding a magnet, and he is only just bringing it closer to this. I'm going to call it a lamp. It's not called a lamp. It's called a electron diffraction thingy. Diffraction gun. Who cares? But as far as we're concerned, there is some sort of phenomenon going on. So he is distorting that image that should have been just well, from our perspective, just a circle, a green circle with a weird cross shadow. So what we can determine from this is that this magnetic field here, so if I just draw it, and it's 3D as well, so it's like coming out everywhere, it's causing, or it's somehow interacting with these charged particles. So if I did it in a different green color, we have these charged particles. So these ones here are going to hit the Maltese cross and they won't get through. But these particles here, they're going to continue on and make that piece right there. Whereas this one, it's going to go behind Maltese cross. It's going to make this bit right here. As the magnetic field comes in, instead of this being basically a straight line now, this itself, I'll do it in blue actually, it would make more sense. So instead of being a straight line behind the cross, that magnet is going to cause it to bend to some circular path. Okay, the actual equation you need to know is basically that force that the charged particle is going to experience is basically your field strength or magnetic field strength times a charge times what's it called? A velocity. There it is. Yeah. You're going to find that I like drawing my velocities like that. So instead of V, I have V with a little, it almost looks like a square root. You need to know what basically B, Q, and R are. And technically F as well, but you should know what F is. F is force. B, already mentioned, that's the magnetic field strength. So magnetic field strength, or MFS. MFS, yeah, MFS. That Q there is basically a charge. You need to know what charge it is, and because this is about charged particles, this is actually the charge on your particle, okay? So that's the charge your particle is carrying. So I say, I don't want to say Q, so that's charge of particle. Essentially, you need to know velocity as well. That velocity again is just the velocity of the particle. So in this situation you have this situation, velocity of particle, can't spell today. And that's basically it. The only things you really need to know is about sort of the paths it's going to take. We sort of Google another image. I'm going to go for cloud chamber. Now, I did particle physics, and cloud chambers were a great thing for me. I used to love cloud chambers. But essentially, what happens in a cloud chamber is... why are these images so small? Essentially, what happens in a cloud image is some sort of supercharged particle, so it's got high energy from basically outside the Earth. So typically these originate from cosmic rays or high energy cosmic rays. These hit a particle in the upper atmosphere and they cause quite a lot of decays, and they're very interesting. But as you can see here, these are the many sorts of decays we get from those high energy cosmic rays hitting basically particles in the atmosphere. You can see here these straight lines, by the way, this is all through magnetic field. So these straight lines coming through this bubble chamber or cloud chamber are basically, we can say, neutral particles because they're not being affected by the magnetic field at all. But can you see here, you get loads of these bends which are, we can say, charged particles but have a lot of mass. So because they have a lot of mass, that force is going to be considerably, the force affecting them is going to be considerably lower than if they had little masses or small masses. And you can see here these spiral graphs or spirals, these are the ones that have essentially very low mass, and because of that, that force from the basically magnetic field is affecting them a lot more. These in particular are basically electrons and positrons. Depending on which way they spiral is the charge. So if you've got a positive charge, it's going to spiral in one direction. If it's got a negative charge, it's going to spiral in the other direction. You can think of it as basically as the current. So the current is basically the flow of a positive charge, okay? So depending on whether your charged particle is positive or negative, your FBI thingamabob, or your fingers, where are they? They're going to point in a different direction for your eye. I'll get onto that in a bit though. But yeah, that's pretty much all you need to know for basically charged particle in a magnetic field. I'm just going to look up what you need next. What you need to know next is that thing you told me about, magnetic flux. Magnetic flux is weird. I'm going to say that now. It's not brilliant. Essentially, the symbol for magnetic flux is this thing here. It's fives. It's basically a Greek letter. But essentially, if you have basically magnetic field, whoops, your magnetic flux is caused, or it's given by, well, first of all, we've already drawn a magnetic field, so it's got to have magnetic field strength. And if I drew a coil of wire in, that there, because this is also 3D, so if I drew it sideways or head on, the magnetic field is actually going to cut through this area. So in order to calculate magnetic flux, I need to know the area as well. So your magnetic flux is your magnetic field strength times your area. Okay, that's the most basic equation for this. There's many versions of this. I'm going to go through it one by one. The next version of this equation is this coil of wire is going to have more than one coil. And every time you add a coil, you're essentially timesing this by another factor. So if I had n number of coils, I would have n number of these areas. So this equation would then become n times my magnetic flux is equal to BAN, or BAN. I quite like that one because it's really easy to remember, BAN. That there, instead of saying n times fives, you could also use fives as a capital. Okay, it looks like this. Sometimes people write it like with these like indents as well. I just wrote with basically I did an I with a circle like that. But that is a capital Phi's, and that capital Phi's is basically equal to basically n times little fives. Little fives is magnetic flux. So what does capital Phi stand for? That's something called magnetic linkage. In terms of knowing values, magnetic linkage is probably more important. It tells you a lot more. Okay. I'm trying to think. Essentially, for the types of questions you'll be given basically some sort of field, and they'll give you the field strength or enough information to work with, and then they're gonna give you an area. Okay, so they might give you a coil of wire like this. So that's I'm gonna say at right angles to that field. In that case, you'll just use that equation. But in the event that they do not give you a set of wires at right angles to this, if I said, let's do it like that. Let's say I had a coil of wires, these ones right here, at this angle here. It's always the angle, basically normal to the plane, the coil. So here's the plane here, and this angle basically from here down to there. Okay. In this case, when you've got a coil of wire at an angle, the linkage equation, I'll do it in terms of n phi's or little phi's, is equal to BAN, but now I need to add cos angle, and it's this angle right here. Again, you might want to write capital Phi's. It doesn't really matter. But yeah, the magnetic flux, the magnetic linkage, that's quite important because it does tell you a lot more. The flux itself is also very important. because that takes you into Faraday's law. So if we move on to Faraday's stuff, essentially Faraday's saying that the induced was mouse induced EMF. I'm just gonna call it EMF. Can't be I, so call it I EMF. The induced EMF is essentially equal to, and this is a differential or derivative. It's going to be n. Technically, I'll do the whole thing. It'll be d of the linkage, so it'll be n phi over dt. So it's the rate of change of the magnetic linkage. But of course, n is a constant, so we can just take that out. So actually, I could just say that it's n times the rate of change of the flux. So your induced EMF is equal to that. I'm not entirely sure. That's probably your next lesson actually, but I'll just go through it anyway. But you might be given an equation, and you might be asked to basically differentiate this or find it from your flux equation. If I just write you out, that essentially becomes your magnetic field times L times V, and that's basically it. L is basically, I'm trying to remember what L. What is it? It's definitely length. It's got to be the length of the wire. So I'm just gonna call it length of the wire. Rod sounds. It might be rod actually. I would say rod wire. But essentially, yeah, that's the magnetic field. That's going to be the length. So if you imagine this scenario, the scenario they like is a plane wing, and the plane wing is cutting through the Earth's magnetic field. So as the basically wing is cutting through, it's got some sort of length that is cutting through these magnetic fields, and it's also got some sort of velocity going through. So the induced EMF in that plane wing is going to be a result from the magnetic field times the length times velocity. Okay, but I'm pretty sure that's going to be your next lesson. The one thing I will talk to you about is Lenz's law, because that's really interesting. I think it might be a Z. Yeah, it is Z. Lenz's law. Oh, it's weird. This was really cool. He's saying, or this guy said, that the direction of the induced EMF or the current is it's always going to be in the opposite direction to basically your I want to say your force. That's probably not a good word. Probably yeah, I've got it. Induced EMF or charge, it's always going to be in a direction to basically oppose this thing here. So essentially, Lenz's law, and just call Lenz's law the lazy law, because what he said was this essentially. So he took Faraday's equation and just put a minus sign in front of it. The reason I'm going to talk about this because I really love this. I'll get a picture. I won't get a picture actually. When an elevator drops in movies, you always think that that's basically scientifically correct. It's not actually scientifically correct at all, because the elevators themselves run off basically these sort of atom boxes along the side here, and that's because these things here are what makes those movie stereotypes wrong. So these black boxes I'm drawing are essentially magnets, really. I can't be bothered to do that one. No, I'll do it anyway. Yeah, essentially, let's look at this scenario where elevator all of a sudden has just snapped, and there we are. So elevator snap in movies, it'll just drop, and at the end, you'll just be left with human pizza. It's true. That's technically incorrect because elevators, as an emergency news lenses law, as this is dropping, those sort of magnets there are running through. They're passing some sort of current, essentially. So these black boxes have magnets, and these magnets are essentially going through some sort of coil wire or whatnot, and it's inducing basically an EMF. Lenses proposed that had to be a negative sign here, because if it wasn't a negative sign, that induced EMF would, in theory, just keep accelerating this elevator into an infinite speed, because you would find this change of EMF. So every time you made a change of EMF, you had a boost in your force, and because it's always changing, you're just going to get boost, a boost, a boost, a boost, a boost, and it'll just fly off. So what elevators do is they make use of lenses law, and this induced EMF opposes direction. So the direction is, in this case, with the elevator, because it's frozen. Is it frozen? Alright, it's frozen now. So I'll just talk. The elevator is dropping, and the induced EMF from those boxes there, those black boxes, actually opposes it. So it's the main force is pushing elevator down, but those black boxes make an induced EMF that makes a force that opposes that direction. That's actually slowing the elevator down, and that's why you wouldn't have an accident in real life with elevators. Technically, because everything can fail, but when you see those movies make human pizza, not true. Sorry, like lenses law. Other than that, that might be enough. I'm not sure how helpful that video was. It might have been good, it might have been bad. So yeah, just let me know, James. Other than that, just let me know if you need more help.